Welcome to the 8th video in our series having a look at GAGE. This particular video we're going to have a look at animation in terms of 2D games. Why is it useful? How is it used in GAGE? And if you want to make use of it to build upon it as part of your project, more than welcome to do so. So as usual, we'll start off having a little bit of a look at the surrounding context for this. And animation is obviously an important thing within games, because games, you want to have objects that show they're notionally alive, that they move around, that they interact, that they do things. So we have to have these entities moving, and playing animations and making use of animations are one of the key ways of doing that. Now, obviously it's a static picture on the screen, but again, you can imagine the objects moving around. And one of the things I want to highlight is that when we're talking about animation here, we're using it in a particular sense. We're not necessarily referring to objects changing their physical location on the screen, but we are referring to objects changing visually how they appear. So there's a distinction here between movement and a change in how something looks. And I can actually show you a video. This is an old classic game, R-Type. And as this moves around, you have objects that are moving. Whenever they, for example, the particles hit it, they actually change to an animation, which is the explosion animation that's happened. So when we're thinking about animation here, we don't simply mean our objects moving around the screen in interesting locations, though that is actually an important part, again, of bringing the world to life. We're thinking here more of the images that are displayed and how those images can change over time to give an animation. So that's what we're using it in the context of this. So that's what we'll be looking at. A couple of videos time we'll have a look at steering. That will enable us to get objects to move around in interesting ways, but this here is about more playing back an animated series to change the appearance of an object. In that context, we'll be making use of Sprite Sheets. Sprite Sheet will contain a whole series of different frames of animation that we will play over time. And by playing that over the right period of time at the right speed, it'll give the appearance then of the character being animated. So it means traditional classical animation in that sense. If you do a Google for Sprite Sheet and you're looking at ones you can actually use inside your game, you'll very quickly realize that A, there's a lot out there, but B, how it is stored can differ quite considerably. In many cases, it'll be simply one frame of animation in each individual file. So you'd have a whole bunch of files that you would need to load in. 3 other examples you can see here. So the image on the top of the sort of female running around, that would be stored in, as an image strip. So here's an horizontal image strip. We have one image inside which we have these 6 different frames. Now, for this particular one, the 6 different frames are stored at regular intervals. If you like, you've taken your image, you've chopped it up into, or your image strip, chopped it up into 6 equal sized elements, and inside each of those you have positioned a frame of the animation. If you find something in that format, that's perfect. That's probably the most easy format you can get in. The example then to the right of this, with the blue sort of Mega Man character, here you can actually see that in terms of the frames of animation, so in the top one we have 7 frames, in the bottom one we also have 7 frames of animation. But because what the character is doing in both of these animations, they differ slightly, the size of it, the length of it, if you were to set it out in terms of a bitmap, differs. So in this case here, because we have to load our animations into memory, because in many games you want to be highly efficient with the use of memory, particularly for older 8-bit games, they didn't, generally speaking, have a lot of white space around each of the frames of animations. Rather, you packed your frames in as tightly as you could get them in, because then it occupied as little memory as possible. So if you're looking at a lot of traditional old-style animations, you'll find that the Sprite Sheets will pack the frames in as tightly as you can. Now, there still will be rectangular frames, but this means if you want to use that type of Sprite Sheet, other than having access to the image, you also have to understand and have a rectangle that defines precisely the location of each frame of the animation, so you can take it out without cutting into the other frames. One then down at the bottom left, you may also find that as opposed to having sort of a single animation horizontally or vertically, you open up a sprite sheet that contains a two-dimensional array of images, and inside that you would actually have several different animations all clumped together. So for example, if we switch down here, you can see that the bottom 4 rows, we have the character walking down, then walking to the left, walking up, and then walking to the right. So depending on how the character is moving, you would play the appropriate element or frames of animation from that 2D sprite sheet. So actually playing back a series of different images is actually quite straightforward. One of the things that will make our animation ever so slightly more difficult from a coding perspective is that we have to deal with all of this variation, or potentially we have to deal with it. You've got two options. You can either say, well, I'm either going to write my code so I assume a certain fixed format. So for example, I'm only going to use horizontal image strips, and I'll assume that everything is regularly spaced. And if you then have some animation data, you need to make sure that it fits into that format so your code works with it. Or you can write your code in a way where you make it, you can support different types of input format, and you have the sophistication built into the code. So it's swings and roundabouts. In terms of the GAGE setup, and you'll see this when we look at the assumptions, it assumes that each of the frames are of equal size. So we're not supporting one where you're packing the things in. We want each of our frames to be equal size, but it doesn't assume a single strip. It can support multiple strips. So it's sort of the bottom left-hand example in terms of the 3 sheets that we see here. Another aspect that we're going to have to deal with when we're thinking about the code of this here. So yes, we'll have our animation data and we'll load that in, but we will probably, depending on what we're animating, you may have a number of different game characters that want to make use of that animation data. So the example here of Mario, and in terms of the yellow highlights, you can have different game entities here. So there's 2 of them. And they're going to be making use of the same frames of animation. Now, this doesn't mean they're animated exactly the same. They may differ in the particular frame that they're displaying at a point in time. There actually may be some random variations around how quickly they play the animation. So you can have variations inside it. But because we want to have that flexibility, when we're writing our code, we want to structure it in a way where if a game object wants to play an animation, that it has a bundle of information that it can use to play that animation, and it's unique to that game object. And if another object wants to make use of the same frames of animation, then it has its own bundle of information that it uses to help it play back the different frames of animation. So we'll see that when we look at the code. So actually, let's look at the code. We'll run the demo first of all, so we get a bit of a feel as to what we're going to be looking for. So inside here, it was in our settings, then inside animation. And we get an array here of 3 by 6, so 18 different animated objects. Now, each of these objects is doing its own thing, and there's 3 different animations that each zombie can actually play. One sort of a standing animation, one a walking animation, and the third one, you can occasionally see them sort of attacking animation. So this is an illustration of 18 objects. Each of them is playing whatever it wants to play, and it is choosing between one of 3 different animations to play. Okay, so that's the setup. Now we can actually let us. So in terms of where this code is found, inside game, miss demos, we've got an animation demo screen, animation demo zombie. That's the thing that was animated. If we go into the screen at the top, I can change number of rows and number of zombies. So I'll just do this so we can see it a bit easier. Run it now. So if we go into here, I'll have 2 rows and 2 zombies. So there's 4. So this sort of highlights then that, okay, 4 different characters. You can see the animation a little bit more clearly in terms of this one here, which is in the idle animation, it's walking, it's that idle animation. If they approach one another, they'll swap around. There's attacked and there's walking. Now, you'll also notice that sometimes the animations or the frames of animation are pointing to the left or to the right, depending on which way the character is facing. That'll come into to how we play it back as well. So sometimes our animation data will be displayed to the left, but we'll want to display it notionally to the right to swap it around. Right, let's have a look then. So what this was playing was inside assets, images, and it was our zombie sprite sheet. So this is the sprite sheet that's loaded in that contains all of these different frames of animations. So if I scroll them down, you can see there's 3 rows, and each of those rows contains one of the frames of, or one of the animations. So the one at the bottom then is the attacking animation, one in the middle is the walking animation, and one at the top is the idling animation. And if I move this across, you can also see that in terms of the different sort of animations that are included within this overall sprite sheet, they're not all of the same length. That the walking animation goes on for a couple of additional frames longer than the other 2. So this is our raw data that we get, our sprite sheet. You'll also note here that each of the frames that we're displaying it in are nicely aligned. They're of a fixed size. So when I load this in, I can assume that each of the frames is nicely cut, both along the X and along the Y axis. And that makes it much easier for me then to be able to identify a particular frame if I'm drawing from this larger image. Okay, so our goal then, we have this image, that's what our base one. We want to look at the code then that enables us to load this in, to understand what we have inside it, to extract it out of some animation data, and then to create demos where we have these zombies and other things appearing on the screen and playing back that animation. So we'll look at each of these things in turn. In terms of classes then, so we've seen 2 of them, the animation demo screen and animation, the demo zombie itself. Now, they're the ones for the demo. In terms of the base code, if we go into our GAGE engine animation package, there's 3 classes inside this, and that's the ones that, if you like, make all of this functionality possible. We have an animation class, an animation manager, and an animation settings. So we'll look at each of these. Now the animation settings, this is going to be a good point to start. It's the class that contains, if you like, details on the sprite sheet. So it tells us about the sprite sheet, it tells us what's found inside the sprite sheet. And that's, if you like, our summary information. We'll only have one of those in the game for the sprite sheet that we've loaded in. So that tells us how to interpret that big image, the sprite sheet. The animation class, each object can create one of these animations. So not that you would. So in our sprite sheet, if we go back to our image, inside this we had 3 different animations for idle, walking, and attacking. So we would have one animation settings that describes those things, and we would have 3 different animation instances. One is for the idle, one for the walking, one for the attacking. So to play an actual single animation, we will wrap up that information within the animation class. And that will also include timing information. So when I had my 4 zombies on the screen, quite to this my demo over here. So 4 different zombies. I've loaded in my sprite sheet. I've got one animation setting file that's sitting there. This particular zombie instance, it is defining 3 animations that it's going to use: the idle, the walking, and the attacking. This zombie over here is defining its own 3 animations. So it has 3 animations for its particular ones, and ditto with the other ones. So the animation class, this is the one we're going to use to package up an individual animation, and different objects can have their own version of it to control back their particular animation. The animation manager then, the name kind of gives it away, is going to be something to help us manage this process. And there's different ways you can do this here, and it really swings and roundabouts. You could have an animation manager that is at the game level, where you register all different animations with it. In this particular setup here, the animation manager is at the object level. So it assumes that a game object will have an animation manager, and it will use that animation manager to help manage its playback. But we'll see that as we go through. Okay, so that's our classes. Let's start off with animation settings. Is the first one. So configuration settings used to define a sprite sheet animation. So it's going to have its information in the sprite sheet. So what do we have? We will have the actual sprite sheet itself. This is the bitmap. So our sprite sheet we will link to through the sprite sheet reference. It contains two integers, number of rows and number of columns. So it tells us for this particular sprite sheet, how should we chop it up? If it was a single sprite sheet, we might say, well, there's one row and there's 6 different frames of animation. And given that information, then it knows the total size of the bitmap, so it can work out just how big each frame is. In this case, there are 3 rows, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 7. Okay, there's 9 or 10 rows or columns as we go across, and 3 rows. So given that information, then we will chop it up into that number of regular size rectangles. So this enables us to understand just how much data we have there. We have another thing then that tells us for the sprite sheet we've loaded in how many unique animations are inside it. So in the case of the one we're loading in, it has 3 unique animations. And then we have arrays for each of those different unique animations. So if we only had one, array size of 1, if we have 3, we're going to have an array size of 3 here. We have a name array size, so this tells us the names of each of the animations. That's important because if we go to the sprite sheet and we say, well, we want to play back the idle animation, we need to have some way of identifying that that's the one we're interested in. So we'll give the names to it so we know which one we're referring to in the bigger sprite sheet. You've got the start frame and you've got the end frame. And that tells you where it starts and where it ends in terms of a frame. So if we go back to our zombie sprite sheet, so if we said then it was total of 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 10 frames across. So if this was 10 by 3, this would be frame 0, then 1, then 2, then 3, then 4, then 5, then 6, all the way across to frame 9 over here, then back to frame 10, 11, 12, 13, 14. So we'll step the frames through. So I would say for my idle animation, it starts in frame 0 and goes through to frame 0, 1, 2, 3, 4, 5, 6, and possibly a wee bit more, 7. So that's where it starts. For the walking animation, it starts in frame 10 and goes all the way through to frame 19. And you get the idea then. So this tells us for each animation strip within it, starting frame, ending frame. So it doesn't all have to be in one row. You can have something that starts one row and overlaps onto the next one, that's fine. But it does have to be contiguously together. So in terms of bounded between a start and an end frame. We've got the total period. So this tells us whenever we're playing these frames of animation back, we want to display them at a certain speed. And by displaying them at that speed, that'll give the appearance of the animation happening. And if you had, for example, like a fireball animation, if you play it too fast, it's there and it's gone. If you play it too slow, it doesn't look right. So for any animation, there's going to be a period, a total amount of time which you play it over, which will look just about right. So inside here, we say in seconds how long you expect to take to play from the start frame to the end frame. And when we're playing back our animation, that's the timings we'll use. We have you can put different ones in here. We're just putting in one additional flag, and it tells us, is this animation intended to be looped? So for example, the fireball one, you would play it once and that's it. You don't loop the thing. Whereas if you had, for example, a torch animation, flickering flames, you would normally loop that. You would play it and it would constantly do it in terms of getting to the end. Let's go back to the start. So this lets us specify if that particular animation is one that is designed or intended to be looped or not to be. And that's the key information that we want to extract for each of the sprite sheets. Now, how do we extract that? We're using a JSON file to do this here. And I'll show you the JSON file for the zombie one. So under animations, zombie. So here we're saying JSON file, we give the name of the sprite sheet. So this is the particular PNG file we've loaded in. We give the number of rows and columns, so it's a 3x10. We say that inside this here there's 3 different animations. Here's the first one, or zombie idle. It starts at frame 0, ends at frame 7. We're going to play it over a period of 1 second, and it is actually designed to loop. Let's go down to our zombie attack. So we give it the name. It starts from frame 20, so it's the 3rd row down. It ends in frame 27. Again, we're also playing it over 1 second, and we're saying that it's not looped. So whenever the zombie attacks and that animation finishes, it will just stand there waiting to do something else. Now, we could actually speed these things up. So if we said our total period was, and let's say 0.2, this will look interesting. So if we change it in our JSON, then it means that whenever we are loading this in and interpreting the data, now for the walking animation, it seems to go much quicker. And again, we're looping it, so whenever we get around to the end, we go back around to the start. So by changing these values in this file, we can control how exactly we interpret the information and how we play back our animation overall. So we'll put that back to 1. So other than having the sprite sheet, we also need to have a bit of additional information that tells us how to interpret and play back the animations contained in that sprite sheet. Back to our animation settings then. If we construct animation settings, it has to belong to a game. So given a game reference, we can load stuff in, we can access our images. And it gives, here we've been asked for the location of the JSON file that tells us about the animations potentially that we're loading in. I'm not going to do this here, you can look at it yourself. Basically it's just a bit of JSON loading. Try to load the file in. If you can get it, get the JSON object out. It assumes that you're going to have a sprite sheet instance, get that. Try to load that particular thing in. If you can't load it in, we'll stop at that particular point. Get the number of rows, get the number of columns. We've now got an array called animations in our JSON file. Go through this and extract out each of the different values. So the name, start frame, end frame, total period, and whether or not we are looping that animation. And that's all it does. So our JSON file, the information we have inside this, basically gets turned into an animation settings file. That's okay. Right, so let's then have a look at the animation class. So we said that animation settings, we have one of those for the sprite sheet. Animation is an individual animation. We will have potentially many of those in terms of each animation in our sprite sheet and each object who wants to have his own animation. So animation then, it will be similar in many respects, but also a little bit different than animation settings. Now, the first thing we have here is facing information, which tells us, do we assume that the animations are facing to the right or to the left? And if you have a look at our sprite sheet, so when we load this in, you can see here the characters, it's notionally all looking to the right. So by default, when somebody drew this, they drew it with the character right facing. That gives us a bit of a problem, because whenever we are running this then, and you have something that is left facing, you need to ask, okay, what do we do when it's actually facing to the left? Now, you could have a completely separate sprite sheet that you load in with all of the images just facing to the left. It's a little bit of overkill. We don't really need it because we're quite happy with the animations looking to the right. We just want to make use of them for facing to the left. And thankfully, we can do that very easily when we're drawing it out. When we're drawing the bitmap out, we can actually just swap the front and the back around. So it then appears, in terms of rendering it, drawing it, that it's facing the other way. And that's fairly commonly done if you have sort of a 2D one where objects don't need to look to the left or to the right. So we have our facing entity here, which says when I'm playing this animation, do I assume it is right facing, which is the default one, I don't change it because that's what most animations are drawing to the right, or if I'm assuming it's left facing, then I will swap it around. Now, different ways you could do it, but this is just the way it's implemented here. We have a name for the animation, fair enough. We have the sprite sheet that we're linking to, so that's also the one that we're playing. We have number of rows, number of columns. We need to know this for the animation because if I want to calculate a particular frame, I need to understand how I chop up the bigger sprite sheet. I have these here included for frame width and frame height. So I will do a little bit of calculation in this here, so I don't need to redo it frequently. This will tell me the actual width and height of each of the frames in terms of the textual values within our bitmap. I've got my start frame and I've got my end frame. This is information for this particular animation, and again I'll be copying that across from the animation settings. Now you could actually link these two. Animation could very cleanly or closely link to an animation set, and you could couple the two together. Just for reasons of efficiency, these things are actually unlinked in that particular sense, so each of them will maintain its own set of values. Don't need to look it up. Now, so far so good. Okay, so frame width and frame height, that's new, but you could have calculated it in the other one. The things then that are unique to this particular animation is the current frame that I'm playing. So whenever I have my zombies, and I'll rerun this here so we go back to our normal speed. Whenever I have my zombies being played, each of these 4 different instances, they will be playing a certain animation and a certain frame of that animation. The current frame they're playing is the current frame. The total period is how long that animation is going to be played over. By default, we take the value that we have within the animation settings file, though you could slow this up, you could you speed it up, you could slow it down. It's entirely up to you how you want to do it, and depending on the character. If the character is moving faster in game or slower in game, you could slow down the animation. We have an important one that tells us when we start a playback of this animation. So inside our game object, when it plays that animation, we will actually take a timestamp for the start time. And if we know when we started playing it, we can actually work out what frame we should be on depending on how much time has elapsed since we started playing it. One here telling us, are we looping the animation? Again, by default, we'll take that from the animation settings. Another one telling us, are we actually playing at this point in time? Animation, we could pause it if the game's paused, or if the animation just isn't triggering. If it's a door opening animation, maybe we're not playing it until the trigger point has happened. And we also know which way we're facing. So it contains a bit of extra information for each individual animation instance to enable us to control the playback of that specific instance. So when we're creating an animation, we actually take in an animations setting file, and it's going to help us do it. If you don't specify a particular animation within this here, it assumes, well, either I'm going to take the first one or there is only one within the file. But in this case here, if you were calling it and there were several different animations within our animation settings, as there is in the instance we're looking at, you would say, well, which one? The 0, the 1st, the 2nd, the 3rd, or whatever animation number is going to be. Thing down here basically just goes through, extracts the values, does a little bit of pre-calculation, so we don't need to keep looking up the width and the height of the bitmap. Stores information, and that's kind of it. We can get the name, we can set the facing. That's important because if our character changes to, it's facing to the right and the character changes to the left, we want to go to our animation and change its facing around. We can get the current facing, we can get the current frame if we need that. We can work out, is this thing currently playing? If we are, we can call the play method, and for calling this we have to pass in the timestamp information. So we'll use this here to commence playback, and there's a check to see, well, are we currently playing? If so, we're not going to do it again because we already have started. If we're not currently playing, we'll store our timestamp, we'll start off with our current frame and we'll set our flag to be true. We can stop the animation playing, and it just says you're not playing. It doesn't change the frame. You'll freeze in the current frame that you're on. And then you have the update method. I'll go through it very briefly. There's another video on animation in terms of how you can go through and pick the appropriate frame, but this basically embeds the code for that. If we're not playing, we return. If we are playing, we work out how long we've been playing for. So it's the current time minus when we started. There's a little bit here just of logic around, am I looping, am I not looping? If I'm not looping and have exceeded my play time, I don't do anything. If I am looping and have exceeded the total duration, then I loop around and I start again. But in essence, it goes through. If we're not looping and we've exceeded our period, then we're simply using the last frame in the animation and we stop playing at that point. So this will end the playback if need be. The else triggers if we are looping. In this sense, we just want to work out how long's it been since we did it. Divide it by the total period. That will give us a number of iterations through. Gives us our animation position. Again, we're using integer arithmetic in this particular, we're using normal, so it gives us a fractional value. We're updating the position here minus this here, so this will make sure it's within the particular right range. And then we're going to our current frame. So this is going to be using integer arithmetic to make sure we narrow it down onto that specific frame. We'll cast it ultimately to an int, and we'll add it onto the start frame. So that's all it does. We drawing method then, we have two rectangles which we reuse, so we don't have to keep creating them just for reasons of efficiency. If we're drawing things out, we've got a little bit of clipping just to make sure the thing that we're drawing is visible on screen. We have one thing here, so when we're drawing out, we need a source rectangle and a destination rectangle. By default, when you're drawing out bitmaps, you draw out the whole bitmap. That is distinctly what I do not want to do in this case. So when drawing this out, I want to narrow things down to one specific frame, one specific region within the bitmap. And to do this here, I go to my bitmap. So when I call this here thing by default, I will get out the region that is visible and tell me how much of the bitmap's visible. Let's assume all of the bitmap's visible. So my source rectangle after get clipped source rec and source and screen rec will be the whole thing. If I divide up the number of rows and columns, I'm going to shrink this down to one individual frame. So by dividing at this point, scales it from the whole thing down to the particular frame that I'm interested in. That's good. Now, it's not going to be located to the right location, but I've got the right width and height for it. I then say, okay, I want to work out for the current row and column that corresponds to the current frame that I'm on. So this is whereabouts in the sprite sheet I want to take my scaled rectangle and move it to. So then I'm mapping onto the right region. And I update my source rectangle now by shunting the right size to the right location inside the sprite sheet. So all of the information here, you need this because we're not drawing the whole thing, we're only drawing one frame or potentially a bit of one frame inside it. So we need to shrink and then position it correctly. So that's what that code does. After this here, we work out, well, are we facing to the left or to the right? If we're facing to the left, we've got a little bit of logic here to swap these things around, just so that it actually looks right overall. But basically the code inside here says if we're facing to the left, then we need to take our current frames and swap them over to the other side. It's not as straightforward as just swapping things around because it depends on the frame you're at and the bits that you're doing that you want to do around. But you can see, you work out the left gap and the right gap depending on if you may have clipping in this, and you then use those to change your left and right of the source rectangle. If you're facing to the right, you don't need to do any of this. You just take the rectangles that you've got out of it and have repositioned. All the hard work's been done then. The get clipped source and screen rec, we don't need to change the screen rec. We're happy with the region that we're drawing to in the screen. We just needed to change the region we're drawing from. So the screen rec is 100% fine. We go to our draw out from the sprite sheet the portion of it that corresponds to the current frame of animation onto the region of the screen that we've worked out. This is the appropriate region to draw to, and we're not applying any tints or anything to it, so it's just null for that particular bit. So that's, I suppose, where the complexity comes into the drawing of it. There is a little bit of complexity on this to make sure that it's drawn correctly from a sprite sheet. That particular version here assumes where you have your game object that you are just the parent one that you're being drawing, so that gives you the bound, where you're passing in a layer and a screen viewport. So this is the version that works if you're using viewports, as you probably should be. There's another bit at the end which just assumes you're drawing directly to the screen. So in this sense, you're not using any viewports, and it's actually a little bit more straightforward. We still have the usual thing to do in terms of working out the bit of our sprite sheet we're drawing from. No difference in the code there. Although the swapping bit, if we're swapping things around, is actually more straightforward. So again, you can see how it does this. It actually just swaps the values around, and that's its job done in that particular sense. And we draw the thing out. So slightly more straightforward if you don't use viewports, but viewports give you a lot more flexibility. Right, that's our animation class. Animation class then packages in these per animation, single animation information. It contains stuff on how to get the right frame when you're doing an update, a bit of logic that will stop the animation playing if appropriate. It contains a few reasonably complex draw methods that will position to the right part of the sprite sheet and will deal with flipping from the left to the right if need be. That's probably the most complicated bit of any of the animation classes that we'll look at. Last one then is Animation Manager. So Animation Manager then, as mentioned, the assumption we have here is that each game object, if it wants to play back animations, will use an animation manager to help it do that. It doesn't have to. It could take the animation class, create it directly itself and use it if it wants to. But in the case where you have several different animations that you want to transition between, for example, for a zombie, there's 3 of them, then Animation Manager will help you with that process. So it's there, it's convenience if you want to use it. So Animation Manager is linked to a game object, which means each of our 4 zombies, their game objects, they will have their own animation manager. Each of them has their own one. Inside each animation manager we have a map which basically contains all of the animations that that particular game object can play and make use of. And we've got a name attached to them, so we can specify which one we want to use. So it's a hash map implementation we use there. We have a, if you like, a sort of not global bit, but it's we have the animation manager has its own facing. So you can go to the animation manager and you can say, well, here's your current facing. It means then that the animation manager, when it's playing back the different animations, it'll make sure that all of the animations use its facing. So it saves you having to update each of the animations in turn. Okay, so this is used then, again, the convenience. And we also know what the current animation is. So out of all of the animations we have attached inside the manager, there's going to be one of them that's currently active. Doesn't necessarily mean it's playing, but it means that this is the animation that you're currently using, or you can trigger the playback off. Constructor then, very straightforward. You just say, okay, what object am I attached to? Job's done. You can get that out if the game object if you want to. You have another bit over here for adding in animations, and so this is using our JSON file. We can say some animation settings. So if we had our sprite sheet with the 3 different animations, we could go to our animation manager and we could say to it, here's a sprite sheet, there's several animations inside it, load the thing in and add each of those animations into yourself as the manager. So it's a convenience method again. So we can go to our animation manager and tell it to load in and store all of those animations. And I'll go to the asset manager, it'll get the asset manager, it'll load and add the animation into the asset manager. So the asset manager then contains the animation settings, it's the thing that looks after those. And then goes through each of the animation settings that was loaded in and extracts out each of the animations inside that. And they get added into this particular animation manager. Using the add animation method, funny enough, you pass in an animation, this is the one we're calling there. It adds it into the hash map. If there is no current animation, so by default when you create the thing, you've no animation, so the current animation is null. The first one you add in by default gets to be put to be the current animation. You can change that if you don't like it, but it means as soon as you have something in it, well, by default you're going to use what you have available. You can set the current animation. You pass in the name of it, and it'll go through, try to get the thing out. If need be, if you don't have a current animation, it'll set the thing up. And if it can't find it, it's going to tell you so. Get the current animation. It tells you what you're currently using. You can remove animations from the file. You can ask, is an animation playing? So they're just convenience methods or utility methods. You can set facing. So this is the one that probably is then useful, that if the character notionally changes its facing, you go to your animation manager and tell the animation manager, hey, I've changed my facing now to whatever this is. And it means the animation manager then will make sure that any other times we're playing things, we're using the appropriate facing. So it stores the facing. If we do have a current animation, it also tells it to change its facing on our behalf. Play then. So anytime I want to play a particular animation, I give the name of it, so it assumes that this animation has already been added to the manager, and I've got to pass in the elapsed time information because I need to know when I'm starting playback from. Again, there's a little bit here just to make sure if we are currently doing something, but we're not going to sort of disrupt that and is equal to the current. If we're told basically to replay the same animation and we're playing it, well, that's what we're going to play. We're not going to restart the thing. It's an assumption in terms of behavior. You could change that if you wanted to. Otherwise then, we get the animation out. If need be, we set up the current animation, make sure the facing is right. And if we can't find it, then we're going to flag things up. Play. If you just call play itself and pass in a time, it assumes you want to play the current animation. If you're not given a particular name, you just say, well, play whatever one is current. And again, similar functionality to the one above, except you know what you're playing. Stop. If you call stop, you stop the current animation, unsurprisingly. Update. So for our animation manager, it's important to call the update method of it inside our game object. So the game object should go to the manager and ask it to update itself if it wants to have the other animations update themselves. And all it does, it says if I have a current animation, well, I'm going to ask it to update itself, and that'll make sure then if there's a new frame needed that we're using the next frame in the animation. Drawing out is actually very straightforward because the animation manager doesn't really have anything to draw itself. It's kind of a virtual object. What it does draw is the current animation. So it goes to the current animation and says, here, draw yourself. And that's it. So our animation manager then is simply a collection of animations and a few utility methods to help us deal with playback. The animation class itself was the thing that contained information on one particular animation, and each object can make use of this for its own playback. And the animation settings were the things that loaded in Sprite Sheets and told us about the types of animation that are stored on those Sprite Sheets. Now, let's have a look at how we can tie all of those things together inside the demo. And we'll start off with the zombie. So zombie is this character that is moving about, that has the three different animations, and it randomly changes from one to the other. So it's a type of sprite. As a sprite, it means we have access to the velocity and the position, and we call the update method. We can give it a velocity and it will move across the screen. So we're using sprite here because we want a moving object. The zombie, we're defining a enumerated type here, so there's three different states that the zombie can be in: idle, walking, or attacking. And we'll have an animation associated with each of those states. There's a little bit of logic here, so state transition probability. So what this basically means is that depending on the state the zombie's in, so the idle one here, it's going to have a probability of transitioning to another state. When it transitions to another state, it does whatever it does in the state. So if it's walking around, still walking. At some point, the probability triggering for the attack probability. So we're randomly changing between these, but we're using our state transition probability to determine just how quickly we change from one to the other, how long we persist with displaying it. We have a zombie facing, so we know which way our zombie's facing. This is relevant if we're updating it has a certain velocity. Depending on the facing, it'll determine if you're moving to the left or to the right. We've got our current state that the zombie's in, so initially they all start off in an idle state. We've got the current facing for the zombie, initially everything's to the right. We're assuming right up here, we may randomize it later on. And we have the animation manager that we're going to create and ask it to look after playback and management of the playbacks. Creating the class, so usual stuff, give it a location, a width and a height, screen that it belongs to. We set up our state transition probabilities. So on average it'll idle for a second, it'll walk for half a second, or every half a second there's a chance that it's going to transition out of this, attacking every 1 second. So this by changing the values here, we can determine how probable it is when it's in a particular state to transition to another one. Here's the bit I suppose is relevant to this talk about animations. We create a new animation manager, belongs to this object. We add in the animation, and that's passing in the JSON file. So we go to our JSON file and we say to the animation manager, hey, there's a bunch of stuff inside this, including a sprite sheet. Load it in and extract out the individual animations because I want to use some of them. And we go to our animation manager and we say then, let's set the current animation to the zombie idle one. So that's what the animation manager will use by default. Now, hasn't yet played it, but that's just the default animation, the current animation that's used. Set facing, we can change the facing of the zombie if we want to. Now if we change it, a couple of things we have to do. We have to set our current facing to whatever's been passed in, and we've got to check here for seeing if we need to go to our animation manager and tell it to change its facing. So we're going to set the facing the animation manager depending on what it is here, either facing to the left or facing to the right, so that whenever we change it for the zombie, we make sure we told the animation manager, hey, use the same setting. We've got a change direction method. This will call, so you know, whenever the zombies approach one another, if they notionally walk into one another, they will turn around and go in the other direction. So whenever they get close, they change their facing or change their direction. And we'll call that from within the demo screen, but that's the method we'll call there to basically tell the zombie, here, go in the other direction. In that case, we swap to the opposite facing, calling the method above, and we change our velocity to the opposite direction as well. We've got a random instance we're creating here just to avoid object correction costs. Update, we need a random one because randomly, as part of the update method, we will randomly determine what we're going to do. We work out our trigger probability depending upon the state that we're currently in. So looking at the current state, we'll get the state transition probability for it, and we'll randomly take a next float, and we're scaling this here by the elapsed time, so that this is a probability per second that we will transition out of that particular state. If we do transition out, we'll pick a new but different state, so we're not going to transition back into the same state, and we store that. Depending on the state that we're in, we'll do different things. So if we're in the idle state, our velocity is 0, we don't move. We go to our animation manager and we say, well, you're using the zombie idle animation. Now remember, when we set to our animation manager, if we set the current animation, and we already are using that animation, so if in the last frame we were zombie idling, and for this one here we say, well, set your current animation to zombie idling, because it's the same, no changes needed, our animation manager will just ignore that request effectively, and then we can trigger the play of it. But okay, so over here, the relevant bit is that if we do change our state, we'll want to say under the idle one, let's change to zombie idle. That'll be different than the current one. Fair enough, it will actually change it. And we call the play method. It isn't going to be played because we just changed it, and that will then start playback of our idle animation. If we're walking, we've got a walk velocity. Depending on the facing that we have, we'll walk to the left or walk to the right. Again, we go to our animation manager and say, here's the animation you want. Because I'm transitioning, it's from a different state. When I do play in this case, it actually will commence playback off it. If I'm attacking, I don't move. I use the zombie attack animation and I play back that. Now, this is really only to do with, so the if here, this code here, will only trigger if I'm changing state. So all of this stuff here about working out the state that we're in, different states, changing the animation and commencing playback, that only happens on a state transition. So most times we go through the update, we're not going to be calling any of this. But every single time we go through the update, we do want to do the things at the bottom. So I want to go to my animation manager and tell it to update itself. So depending on whatever animation I'm currently playing, I want to let that animation iterate through onto the next frame as whatever is appropriate. And I also finally call the super update method. So this is a sprite. If I call the update method a sprite, it'll look at the velocity, it'll give it a new position, it'll move it across the screen. So that deals with the movement. And that's where all the complexity really resides in that class. You can see how things are loaded in, how animations are set, how animations are changed. If I'm drawing things out, I simply go to my animation manager and I tell it to draw out whatever the current frame of the animation is, and it does that. Final thing to look at then is our animation demo screen. So depending on whenever you had in here, you can specify, we could do 33. So you've got your normal back button, you've got details of how many zombies you have inside it, and again you can pick this to be whatever value you want. Here you have an issue because you can't fit that number into the row, so we're having them all sort of squished together at the side because they're trying to remain separated from one another. But maybe go back to our lovely 3 where it looked okay. So 6 rows, 3 zombies. We have a 2-dimensional array of zombies where we can store them inside it. Here's the constructor. We create our back button. We need some way of going back. We work out zombie height and width. We're doing a little bit of an assumption here, but it kind of works in. So we're going to work out the height based on the number of rows, and we're going to give it a width, which really is a scaling based on the height. So it sort of has sort of the right sort of aspect ratio for the zombie overall. We work out a bit of spacing between them then, so we're going to try to position them, and we can position them with 6 and 3 in the row. So we're going to try to position them evenly across the different areas, so they can then trigger and walk without getting in the way of one another. For actually creating the zombies, we're going to do the following. We say, okay, we're going to do it for each of the rows and each zombie in the rows. We're going to create a new zombie. We give it its location, so we're going to space it out. The fixed width and fixed height are all of the same size. And then finally, we're going to give it a random initial facing. So we did say at the very start, whenever we were creating our zombies rather, inside here, if we just create a zombie on its own, by default it faces to the right. Over here, whenever we're creating our zombies, we're going to create one. It'll have the right facing first of all, and then we're just going to randomly change it to the left or to keep it with the right. So again, looking in different directions. Store the zombie in our array. Fair enough. Update. We don't do that much, to be honest. If the back button's been pressed, we go back. Other than that, we go through each of our zombies. We say, okay, there's rows and there's zombies in each of the rows. Get the zombie out that we're referring to. Tell that zombie to update itself. So it'll do all of the stuff that we saw about maybe changing its state, updating the animation manager, things like that. The bit we have down here is the collision detection aspect of it. So if we updated the zombies, they potentially moved, and they're potentially moved in a way that are overlapping with one another. So we've got a little bit of code here just to go through the zombies in the particular row that we're looking at, not comparing ourselves with ourselves. Using the collision detector, we'll look at it in a later talk. If we do have any type of collision, so if it's not equal to none, so in other words there's some type of collision, then we go to the zombie that caused this and we tell it to change direction. Another one then, so there's also possible that other than zombies colliding with themselves, if we have a zombie that walks up to the edge of the screen, and potentially is going to leave the screen, or the viewport in this particular case, we want it to change as well, so things don't wander off the screen out of the way. So there's a bit here we get in the bounding box, comparing it to the well, basically 0 or the default layer viewport width. So again, if it tries to leave out of the layer viewport, we will turn it around so it stays inside the layer viewport. Drawing it, very straightforward. We clear the screen, we go through each of the zombies and we tell them to draw themselves, and we draw the back button. And that's it. That's the whole demo together in terms of what it does. Wrapping all of this together then, animations, useful things. They get good animations. They can really bring the game to life, give a lot of character to the game. One of the things that can be a bit challenging is just in terms of that animation data. It can come in different formats, and you either need to restrict yourself to a certain format or get the images in and do a bit of pre-processing. This could either be changing the actual images so they are regularly aligned, or when you're loading things in, do a little bit of manipulation at that particular point. So, you know, swings and roundabouts in terms of how flexible you want to be versus how constrained you want to be. Generally speaking, we'll also need some type of animation playback management, just to control how this happens and how we deal with multiple different animations all playing at the same time. But in the grand scale of things, it's not really that difficult. So hopefully of use.